this presentation titled Do Cell-Penetrating Peptides Alter the Fluidity or the Elasticity of Lipid Membranes? A brief beginning of mechanical and rheological properties study. Cell-penetrating peptides, commonly known as CPPs, are cationic polypeptides with a large electrical charge. They are found in different living organisms and fulfill the common goal of creating a favorable environment to overcome the limited permeability of membranes. This property gives them the ability to be effective carriers for intracellular delivery purposes, especially in medical therapies. The first stage in this process involves CPP's adsorption at the interface and possibly the modulation of the biliary mechanical and rheological properties, which will drive to an interfacial remodulation. Non-arginine, commonly known as R9, is widely used as a CPP model. Previous work compiled by Di Pizza et al. In 2014 suggests that CPP adsorption and subsequent insertion would mildly perturb the bilayer's structure. This behavior has been clearly described by Grossi et al. In 2019, but with experimental analysis of giant unilaminar vesicles. In order to measure the mechanical perturbation of the membrane caused by the peptide, these authors quantified the fluctuation of the vesicle shape and the relaxation time of highly deformed vesicles, evidencing that CPPs soften the lipid bilayer. However, it remains to be seen such behavior can be attributed to the change in the bending rigidity or to a change in the membrane viscosity. This indicates that the interaction between CPPs and bilayers drives a rearrangement on the membrane structure, being CPPs not completely innocuous to membrane integrity. In this way, our work aims to describe the molecular basis of the interaction between R9 and model membranes and whether this interaction modulates the bilayer mechanical and rheological properties. Our systems consisted on a solvated bilayer of phospholipids with physiological sodium chloride concentration in an orthorhombic box with periodic boundary conditions. We incorporate the R9 in the aqueous solution. We perform MPT molecular dynamic simulations using GRUMACS package and Martini-Kurzweil force field using polarized water. This force field has the advantage that allow us to simulate bigger systems and for longer times than atomistic models. With analytical purposes, we use the capillarity wave analysis method. This approach uses the phosphate head groups to set an intrinsic isotestic surface at each hemilayer interface through the trajectory. A fluctuation analysis by Fourier transform in the mesoscale enabled us to estimate the bending rigidity modulus of the coupled ondulatory mode of the membrane. On a first step, we assayed R9 interaction with lipid bilayers of different compositions by umbrella sampling method. As expected for the strongly electrostatic interaction, negatively charged lipid content in the membrane increased R9 affinity, while no affinity was observed toward neutral membranes. In all cases, interfacial adsorption was the thermodynamically preferred process, while a barrier was computed for the translocation. In order to validate the capillarity wave analysis, we applied it to a pre-equilibrated bilayer of DPPC with 1,352 phospholipids per hemilayer, simulated through 20 nanoseconds. These simulations were performed at 288 Kelvin and 323 Kelvin, recreating the gel and crystalline liquid phases respectively, with well-characterized viscoelastic differences. Gel phase exhibits a lower area per lipid than liquid crystalline phase. The elastic modulus obtained by fitting the simulated data was, as expected, significantly higher the gel phase than for the liquid crystalline phase. After that, we moved to the target membrane of DPPC and DOPG with 1,352 phospholipids per hemilayer. These systems incorporate from 25 to 100 non-arginines. We are currently applying the capillarity wave analysis to the membrane alone and with different CPP interface occupation fraction in one or both hemilayers, in order to evaluate effects of CPP bonding to the bending rigidity of the membranes. On another approach, in order to assess the dynamically component of viscoelastic effect, we are preparing curved bilayer using lateral compression in order to compute the relaxation time when tension is released. Thanks for all of you. I hope you have enjoyed, and I want to say thank you for all the team that is behind of these bilayers.